Today, we're diving into a really fascinating corner of artificial intelligence. We're going to break down how a machine can actually master a task, not because someone programmed in all the answers, but by learning from its own trial and error.
So let's just start with a puzzle that's really at the heart of modern AI. How in the world can a computer learn to win a game when nobody ever tells it the rules? How is that even possible?
Well, the answer lies in this incredible field called reinforcement learning. And it's a super powerful approach that's completely changing what machines are capable of.
You see, unlike a lot of other machine learning that needs these huge pre-labeled data sets to study from, reinforcement learning is all about learning from the consequences of your actions. It's truly learning by doing.
Okay, so what does that actually mean in practice? The core idea is surprisingly simple. You've got an agent, that's our AI, and it lives in an environment. It just tries out different actions, and for every action, it gets either a reward or a penalty. The whole goal is to figure out which string of actions leads to the biggest possible reward over time.
And this right here, this is the engine that drives the whole learning process. The agent takes an action, the environment changes and spits back a new situation and a reward, and then the agent uses that feedback to decide what to do next. It's just this continuous loop of action and consequence over and over again.
But this brings up a pretty important challenge, right? Memory. How does an agent actually keep track of what works and what doesn't?
To make this really concrete, let's look at a classic example, a game called Frozen Lake. Our little agent starts in one corner, and its goal is to get to the gift on the other side, all while avoiding the holes. Seems simple enough, right? But here's the kicker. The computer starts with absolutely zero knowledge of the rules.
The original way to solve this was something called a Q table, and honestly, you can just think of it as the ultimate cheat sheet for the game. For every single square on the board, each state, it keeps a score for every possible move, up, down, left, or right.
So, how does this cheat sheet get filled in? Well, the agent uses a special math rule called the Bellman equation. After every single move, it looks at the reward it just got and also tries to estimate the potential for future rewards from its new position. It uses this combo to update the score for the action it just took. And after thousands and thousands of tries, these scores get more and more accurate.
And here's what you get after all that training. The cheat sheet is completely filled out. Now, no matter what square the agent is on, it just has to look at its table, find the action with the highest number, and boom, it knows the best possible move. It has totally solved the game.
Now, this Q-table method is brilliant for simple little worlds like Frozen Lake, but it has one massive, completely game-breaking limitation. I mean, what happens when the game isn't a tiny 4x4 grid? For games like chess or Go, or forget games, for real-world problems like driving a car, the number of possible situations is, well, it's astronomical. A cheat sheet would have to be bigger than all the hard drives on planet Earth. It's just not going to work.
This whole scalability problem was a huge roadblock for a long time, but then researchers had a breakthrough idea that just completely changed the game.
The big breakthrough was to just get rid of the giant cheat sheet altogether. Instead of a rigid table, they gave the agent a deep neural network, a flexible, decision-making brain that could actually learn and generalize.
And this is what we call deep Q learning. The agent feeds the current state of the world into its neural network, and the network then predicts the best action. The absolutely crucial difference here is that it can now generalize, making smart decisions even in situations it has never, ever seen before.
This shift from a simple lookup table to a predictive brain is what finally unlocked reinforcement learning for the real world. All of a sudden, this trial and error learning could be applied to incredibly complex problems, everything from robotics and autonomous cars to finance and even medicine. And the impact of this new approach, which we call deep reinforcement learning, was nothing short of a revolution. It just sparked an absolute explosion in research and development. The field just caught fire, with breakthroughs happening at this dizzying pace as scientists and engineers started applying this powerful new tool to, well, everything you can imagine. The combination was so powerful that David Silver, one of the lead developers of AlphaGo, famously summed it all up with a simple formula. AI equals reinforcement learning plus deep learning. This has basically been the recipe for so much of the incredible progress we've seen in AI in recent years.
And this brings us right back to where we started. We began with simple games, but by enabling machines to learn from their own mistakes, we've unleashed a technology that is now tackling our most complex challenges. The question really isn't if it can solve them anymore, but what problem is it going to solve next?